Hi there. I've got a bit of a story for you about the number 10 and a way of looking into the number 10 in terms of dozens and in terms of shapes, right? And we're all, I suppose, most of us at least, mostly familiar with 10 because we have the 10 fingers of our hands and 10 toes on our feet. So it's reasonable to think of 10 in sets of 5. And I would say that this is a key feature of the metric system as well. Now, I've been deep diving into a different kind of framework, a spherical one, Synergetics, and the way of the spheres, and in that place it turns out numbers have a lot more resonance within them when we look into them not in terms of 10, so decimal, but in terms of dozenal. And yeah, so I've got a full bag of little bead Synergetics here, all kinds of shapes of 10 spheres each. And I'm gonna go into those and tell you a little about them. But first, to see why I looked into them in the first place, I had these 10 brass rods that came back to me. 2 got lost, so it's 10 now. And I was holding them as tightly or as closely drawn as I could, right? And they would reveal this pattern here, where you can, I think, make out that there is 3 on the top, 4 in the middle, and 3 on the bottom. 3, 4, and 3. So that's 6 around 4, really. But I also know that the number 10 has to do with a triangle, and most famously so because of the tetraktys, which is an ancient mnemonic device used by the Pythagoreans to really comprehend the cosmos in a very synergetic way. And in the case of the rods, if I hold them like this, they become that triangle arrangement. And in the case of the tetraktys of Pythagoras, they would do it with pebbles. I've done a bunch of videos on that. Yeah, but this is really, it's fine, you know, these rods or pipes behave in the same patterns and ways as would, for instance, batteries or anything really of these round things. But that is because the spheres do. And now I'm gonna show you these 1,001 kinds of shapes of 10. And I've already shown you 2 of them, because we find this one, which is the first one I showed you with the 3, 4, 3. Yeah. And we can also see that it's almost like a hexagon, or it is like a hex here, 6 around 1, and then there's 3 more on one side, which kind of makes it into an overlapping 2 hexes. So in the middle between them they share a pair of eyes that the Greek called vesicopaises. Perhaps that's Latin, but anyways, that is the overlap there. And we can look into the shape also in terms of its area and its circumference, and we'll find that we have here on the top 5 eyes, 2 from the top, 3 from the bottom, that's 5, and another 5 on the mirrored on the bottom. So it's 10 eyes. 10 eyes of area, and the circumference is, let's count these steps, these fingers that the thread is jumping, the intervals around is 1, 2, 3, 4, 5, 6, 7, 8. 8. So we got 10 eyes with 8 fingers around them. Let's look into the triangle for a second here. Now this looks like the tetraktys, as it is popularly known. And it is again 10 spheres. We could say the way usually it's looked at, it's 1 giving a point, 2 giving a line, 3 if we put them together give a triangle, and 4 give a foureyes put together. That's cool. There's lots of more patterns here, but this also shows a kind of pattern in terms of dozenals, because we find that 10 in this case is 3 around 6 around 1. 3 around 6 around 1. That's 10. Also, this shows us how in Synergetics we account for areas in eyes, in triangles, and that is, in the case of a triangle, it's the operation to the second power that we're used to with square numbers. So we have 3 by 3, and that is 1, 2, 3, 4, 5, 6, 7, 8, 9 eyes. 9 eyes in the whole thing. So this has an area of 9 eyes, and the circumference, it turns out, is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's also 9. 9 eyes for 9 fingers. Remember, we just had 10 eyes for 8 fingers. So there's a balancing going on. And we can turn the balance into another way, where we put these together in, well, any of these ways. So this is also 10 spheres, 5 on the top and 5 on the bottom. Right? And between them we find 1, 2, 3, 4, 5, 6, 7, 8 eyes. So this is an 8 eyes. In this case it's just a line of them. And 8 eyes is the area, and the circumference is 1, 2, 3, 4, 5, and another 5 on the bottom. That's 10. So now we have 8 eyes for 10 fingers, where in the beginning we had 10 eyes for 8 fingers. You see how the scale is tipped the other way, and the balancing point is the triangle in the middle. But this is not all, because this can wrap, and we'll return to that in a second. That's another shape of 10. But first let's see a few more of the variants that these 8 eyes can come in, because there's plenty. And 11 of these patterns of the 8 eyes are usually known as nets for the 8 eyes in mathematics. So for the octahedron, you can draw on a piece of paper, a cardboard, a piece of fabric, something that gives you sufficiently high frequency material so that you don't need to bother with the tiny triangles in it. You can just draw these patterns on, cut them out, and fold it into a I had one just now into these containers here, like this. This is an 8 eyes of cardboard. Let's see. I think this one doesn't fold into one. That's gonna be next. But this is another way of putting the 10 spheres together, where we have 4 eyes here and 4 eyes there, so it's 8 eyes again, and the circumference is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, 10 fingers for 8 eyes, so it's on that scale of the balance. Here is another way to have them, and this is really beautiful, and it is one of the possible patterns to draw out an 8 eyes net that one wants to fold up into a box like this, for instance. This has added ears around the eyes, but that's a story for another day. And when I say that you can draw this out, you can think of every one of these spheres as one point of a of putting your compass in the paper, on the paper, right? Never mind. You probably have seen the compass, and if not, you should, because they are useful and incredibly simple but powerful, virtuous tools. Anyways, you take a compass and pattern out this with your compass on the material, right? Every one of these spheres is one circle that you draw, and between them you can draw these triangles, and cutting them out they fold into the 8eyes. So that's another 10. And here we have 4eyes and 8eyes. It's 8eyes, and the surrounding is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 fingers. Again, 8 eyes for 10 fingers. And this one here is perhaps my favorite of all of these. It's kind of, I call it the butterfly. And this one is also one of the possible patterns to draw to make an 8eyes, because if the triangles themselves fold up in that. This one wouldn't, by the way, because it has too many beats, right? It's too many spheres present. And in an 8eyes, some of them would need to overlap, which is possible with paper or cardboard, but not with this. But again, we have 4 eyes here, 4 eyes there, and the circumference is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, another 8 eyes for 10 fingers. Alright, so that's all those. That's the cat. That's all the many kinds of 10s. The shapes. Oops! Oh no! She tried. She'll try again. Oops! Oops! You can do it. Hop! Yes, there she goes. Alright, so I said before, when we were at this place, that this can wrap up like this, which is kind of like my band here. And when we do that, we get this one, which is also 10 spheres, but 10 spheres in a ring, right? And if we were to add 2 beads to this, one on the top and one on the bottom, we would get the dozen around non-spheres that we have in the dozen and 8 eyes, or the icosaops. So that's, take one of those and remove the 2 polar spheres of spinability, and you get this ring. And counting the eyes on this, we would get another kind of strange arrangement where we have 10 eyes all around and 5 fingers on one side and 5 on the other. So we get 10 eyes for 10 fingers. Remember, the highest we had so far was 10 eyes for 8 fingers. But this is nice. Oh, and mind you, when I count the eyes on all of these, they count double, because all of these have a double membrane. They have one side of them and then the other. And once now that we begin wrapping these spherical structures up, we actually get the case that one of these membranes, one of these sets of triangles here, becomes the concave and one is the convex. So the convex is being stretched and the concave is being reduced. And that gives us stuff like this. This here is a piece of tetrahelix. And the tetrahelix is a fabulous, fabulous thing. There's people who've been studying it in depth. And we can see here that this is the simple-most point of origin for something that life has played out into, something like the genes, DNA, RNA, these things coming in helixes. And this is a tetrahelix, and as such this one has 1, 2, 3, 4, 5, 6, wait, 1, 2, 2, 3, 4, 5, 6, 7. This is 7 quanta, 7 foureyes in terms of volume and in terms of what these make up, like so. And that is given with a complete set of 1, 2, 3, 4, 5 times 3, so a dozen and 3 eyes. Okay, that's this tetrahelix, and I can tell you, I can promise you that there is most likely many more and innumerable, perhaps even combinations of spheres like this. Hold on, I'll be back in a second. Yeah, as I was saying, there is most likely a very large, if not even, yeah, infinite number of ways to put together foureyes without any complementary eighteyes, which would be the way that the isotropic vector matrix grows, and that's what we're gonna look now to. So I did not dive deeper into the, I call them the phi-isotropic vector matrix, where all the golden ratio goes on, you know, like, yeah, foureyes without others between them, or eighteyes without others between them. There's a lot of stuff there. Not to take that route now, I instead want to take us into the continuation of the pattern that the Pythagoreans had seen in this, according to legend, or according to the scriptures, the books, where again it's said that this would be the monad, the point, supposedly without, or according to Euclid and Plato and co, without body, then the line between 2, 3 that come together and make a triangle, and 4 coming together to make a foureyes, which is supposed to be then a volume of space, so that would make it a 3-dimensional tetrahedron. But that is not really what I would speak of with these things, because yeah, I did just do it just to reference this to its traditional way of transmission. But I would like to emphasize that this stuff is really basic synergetics when we do recognize the presence of the spheres. And the easiest way to find the patterns of space-time is by watching the spheres behave, rather than by abstracting them away and saying it's just points and infinite lines and infinite planes and so forth. These aren't infinite, and they're definitely not separating anything. They're always binding together, insides and outsides of systems. So let's see what happens if we do take 10 and not just take them line by line with 1, 2, 3, 4, but to take them all on top one another. We actually get something that is incredibly significant, which is the two-frequency foureyes. And this is something I had brought up in the many videos I've done before on tetraktys, because I think at least this was absolutely known to Pythagoras and his people. And with this they would have also recognized the complementarity of spacetime, where we have not only the complementarity of inside and outside of this system, but we also find that this big foureyes is made up of, or agglomerated, by, how do I show you, 6 in the middle, who create this kind of structure. This is an 8eyes, and we find that in the middle of this big thing. We don't see it necessarily in whole with this configuration, because the eyes between the spheres are tiny, but there is here these 4 outer ones, which can be the same 4 that make a small 4eyes, spread apart and surrounding those 6 between them, remembering an 8eyes, which has a volume of 4 quanta. Let's call that a qualia. So 1 qualia with a volume of 4 quanta, and then 4 tiny quanta, 4 tiny 4eyes on the corners here. So the overall volume of this is 8 quanta. Now that is significantly so, because significantly so. It is significantly significant. Sometimes you just get stuck in words, but never mind. This is important because the same way that we have seen how the so-called square numbers, the second power function of numbers, comes from the triangles, as in here 3 by 3 giving us 9 eyes. Similarly, the volumetric operation of third power comes from the same spheres, but in 4-dimensional spacetime. And why 4-dimensional? Because there's 4 planes of it, and those are always evident and present. And in this case, this is a volume of two fingers here, because it's 2 frequency, 2 intervals, 2 times 2 times 2, which is 8. Right, so this is the same thing as saying 2 to the third power. However, it does not just account for the presence of a uniform cubic volume where everything is the same everywhere, but this is also qualitative, not just quantitative, because it tells us about the qualia as well, the qualia volumes in there, and about there's another direction of spacetime that we get to now, next up. Right, so this is like a beautiful, beautiful, beautiful thing to see. Yeah, this one can also come together with that, and I just thought of that when I had these created. So this would be the tetraktys in a plane, as it's familiar with to people. And this is the tetraktys stacked into the 2-frequency 4eyes. And what happens if we put them onto one another? Well, that happens. We get a 3-frequency 4eyes. And, you know, space-time continues. We could look into the qualia and quanta of that. I can tell you the volume of it would be 3 to the third power. 3 times 3 times 3. So 9 times 3 is 2,003 volume. And more things of fractals in there. Just ask if you want to know more about that. But, you know, this is something really, really, really cool to see as well. But I also said, oh, and this is actually where it begins in a way, because now that I've stuck these together like so, you can see how on top of this triangle I put this center sphere here of that hex. Now with that I have the opposite pole of this axis of spin present, right? So there's a tip here and there's a tip there, and that tip there is what we have in this case, where I moved the tip of our two-frequency foureyes onto the other side of it. So this is still one 8eyes with 3 foureyes around it, and the fourth foureye sits on this side of the thing, which is just the other way around in a way here. Up, like so. I can hold on to the tip on one and on the other, and then it shows top and bottom. Alright, so that's a first foureyes that is the inverse direction, right? And we can move that around the 8eyes a little more, and another way to have it placed would be like so, where we still have the base of the foureyes, the two-frequency foureyes, but the tip rolled down to the side there, which gives us this nice axis of spin as well, where again you can see me holding on to those 2 poles that I was just speaking of. And between these 2 poles we have one sphere on the top, one on the bottom, and the 6 between them, the 8eyes. And that complex is a dozeneyes, and yeah, a lot of beautiful things to be said about that. Never mind. Let's go see where else we can drop those spheres, and here is another way to do them, to put them together. And you can see here, this is kind of like half of the 2 dozen around 8eyes, also known as the Merkaba or the star tetrahedron, where we have an 8eyes here in the middle, just as before, and now we placed 2 foureyes here and 2 here. So that's 2 positive and 2 negative coming together. And this is interesting because all the while now we only had, on this case we only have the small foureyes that point that way, and on these other ways we have 3 of those pointing that way and 1 here pointing the other. On this one also we have 3 pointing this way and 1 pointing the other. And now for once we have 2 pointing one way and 2 pointing the other. Maybe if I hold it like so, that's a little more clear, because suddenly it doesn't look as square anymore. This one pretends to be cubic, but there's no cube here. Yeah, but you see how 2 of these point one way and the other 2 point the other way. Alright, and still the volume of this is 8 quanta. But here's the last one of them, the 1001th that I've come across, that I thought of at least. I mean, again, I'm pretty sure we could probably find another way, and probably more than one more way of putting together 10 spheres. But these ones, to me at least, felt somewhat significant, and I was happy with the 12 of them. But thinking of one more made the whole thing a lot more round, because this turned out to be this beautiful thing. And this is half of the vector equilibrium. In other words, it is half of the 12 around 1 spheres, which I made one of them like so. This is the vector equilibrium, and you see this is 1/2 of it. We have the lines are a little run to the side there because it doesn't really like to be in equilibrium. But you see that triangle of spheres, that's these 3, and on the top there we have that triangle, and on the bottom wait, here's the 3 spheres, right? And between the 3 spheres is the 4 that look into the half 8eyes. And on the other side here we have, or on the bottom of that, we have a 6 around 1. Yeah? I probably, the other, you know what, I wish I would have brought those, but I already have them in another bag somewhere. But just the other day I created 3 kinds of variants of the vector equilibrium, so to speak, because there is having a dozen of these beats around one, that's the vector equilibrium as such, where I might have the magnets here, so no. No, never mind. A dozen around one, where they can't really move all that much because there's the nucleus in it. Then there is a dozen around none, which isn't omnitriangulated, so it moves like this. This is a higher frequency of it, that kind of membrane. And then lastly, a dozen around none, where it's omnitriangulated like this. Showed you before the dozen around none, the dozen 8eyes. And that's really beautiful, you know, those 3 embody so much between them. And I was really amazed to realize, I mean, it's kind of obvious when you think about it, but to realize it is another thing, that 10 spheres can also make that half of the dozen around one, because we find here we have 3 around or on top of 6 around 1, right? And on the vector equilibrium it would just be, I can show you like this, I can show you, we can put them here on the other sides, other eyes. Now we have the dozen around 1, the vector equilibrium, which is also the 2 dozen 8eyes. And we don't have those. Oh, I can also make a 4th of those. That's nice, because there's this one which is polarized. I will do that now that I think of it. Thank you for the reminder. But now, to wrap this whole thing up, let us think about this configuration in terms of its volume, and then we can find that this is really 3 4eyes sitting with a shared corner in the middle, a shared sphere in the middle, and that one is also shared by 1 4eyes that is pointing the other way, pointing inwards from the top. So there's 3 pointing up, 1 pointing down. That's 4. And between them we have these voids that are half 8eyes. And if we wanted to account for them as volume, then they would be 2 quanta. Because 1 qualia, 1 8eyes is 4 quanta. So this is half of that, which is 2. And 3 of those give us 3 times 2, a dozen. 3 times 2, 6. 6. Plus, remember, the 4 quanta is 10. So how about that? We suddenly have a volume of 10 quanta out of 10 spheres. That's pretty wild. Given that usually you get 1 quanta for 4 spheres, if you only have that. And now we have 10 spheres and get a full 10 quanta out of that. Or really not a full 10 quanta. 4 quanta and 6 half qualia, 6 more. Yeah, anyways. This is really big. This is voluminous. Why is that? Because it is very close to a sphere in its own right. Because the pattern that this grows this is the same kind of fractal pattern that we have seen with our friend the foureyes here. It's just centered around a bead, centered around one sphere, which is the same kind of one sphere that we see when we put these two together, as I showed before, because they're in the middle of this big eye is the 6 around 1, right? And that is the nucleus of a vector equilibrium. Well, all right. I think that was quite a lot of perspectives on the number 10. I hope I spoke to most of the things, at least I spoke to most of the things that came to mind so far. That is not to say that this is the last of it. There's probably more to this. And if you can think of something, please let me know. I am genuinely interested in these things, for whatever reason. I mean, the Pythagoreans were too, for whatever reasons. And I think Buckminster Fuller was. And I guess the reason for being into this, from my point of view, is that I have been thinking in the number 10 in relation with cubes and squares and metric system all my life. Right? I was born into that. And I could never really understand why anyone wouldn't have a metric system, because it made so much sense with tens and hundreds and thousands and the halfway points at 5. Right? So why would anyone have something like a system where one has a dozen of something as a unit? Well, one thing is we can just count further with our fingers, right? Because we cannot only just take the 10 fingers as at face value. We can also say we have these 4 fingers and each one has 3 digits. 4 times 3 is a dozen. So it turns out people have for a long time known that we can count with the counter being the thumb. We can count 0. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, a dozen. And that would be the first dozen. So I can count single digits here and dozens on the other hand. So counting up here, I get 1 dozen, 2 dozen, 3 dozen, 4 dozen, 5 dozen, 6 dozen, 7 dozen, 8 dozen, 9 dozen, 10 dozen, 11 dozen, a dozen, which is a grow. And a grow is also known as 144 in decimal numbers. Right? And that is already staggeringly more than 10. But we also still have a dozen more on this finger, so we can count all the way up to a grow and a dozen, which is a dozen and 1 dozen, which is a Fibonacci number for whatever reason. You know how these things pattern out? But this is a way of locating and thinking of the number 10 that is so identified with the cubic and metric, and take that instead from a point of view of the spheres, a dozenal point of view. Yeah, that's what I do, you know, and I use my dozenal numbers to make sense of these things. I can draw out these patterns and reason about their numbers. And the number 10 in this system of ours looks like this there. Those 3 lines around that dot. And that is because in the 10 spheres in a triangle there is the on this one. Yeah, anyways, this is already way too deep. And if you do want to know this bit about the number 10 and why it looks this way, alright, ask me. I will tell you. with pleasure. But I think this goes to show how it is quite fascinating to know and to figure out, figuratively and actually, in reality, what members of space-time do when they come together and hang out, right? Because we can learn a lot of that from that, because we are members of space-time too. We are members of the universe. We are kin among kinship Earth, and we have a place in the middle of all of this. We've just lost a frame of mind that gives us access to that middle, to that center, to the point of balance, and to the change and movement that comes from that. But it's not lost and gone. It's actually around. We just need to talk a little more about it and get our hands-on experience of this. There's nothing I can think of that could substitute for this, really, because allowing the things to play out as they do allows us to learn about who we are and how things go within our kinship of universe. And stuff like that, tetrahelix, these things are resonant with so many layers of our existence, from the microscopic, from the nuclear, atomic, and even quantum level. It's all the same patterns throughout biology, throughout chemistry, throughout biology in terms of cells and their organisms and the fascia in our bodies and the structures of our bodies, all the way up through the trees and the canopies, through the level of planetary kinship, through the level of solar systemic kinship, through the galaxy and the clusters of those, and the whole thing is dancing along these lines of interrelationship, not interdependent. Dependence being there's a big one and the small one hanging on to it, which kind of makes it seem as if the big one would never be influenced or moved by the small. But we are living in compendence with one another, intercompendence. Compendence is the hanging together in relationship. And every one of us is member of this. And we all have the option and choice to not only mind the mindless, disembodied, lifeless, solid geometry of Euclid and the Greek and the system of Babylon and its subsequent abstractions of mathematics that are useful in their own way, but out of tune with universe and the way that universe is playing these games. We can play in tune with that very easily, and it's a great lot of fun and very wholesome. So just to round this all up with the 1001 kinds of tens in mind, here's a little poem I came up with yesterday. Now, universe is an animate, ongoing unfolding of the fractal forest of spherical spacetime structures, embodying and membering the graceful geometries of the Tao. Yeah. I hope you had fun. I did. I hope you were inspired by a little of it. I was. And even just that was worth it. And even more so if it meant something to you too. And if it does, please let me know. Please give me feedback and resonance. And also share this with other people that you think may be, in whatever way, intrigued by this. With that, thank you for your attention and intention and the integrity of our communication. I hope on that, I trust in that, because I'm really just talking to myself on a camera here. And I'm talking to the spheres, among the spheres, with the spheres. And they tell a great number of tales and stories. And it's fun to listen to them. And fun to put them in words. Yeah. Alright. Take care. Bye-bye. Peace.